Hi, everyone. I wanted to check in and say hello. I am putting together a couple additional extra videos that describe how you might do a few extra kinds of analysis. These might be helpful as you do your final project. Not required, but kind of neat. Today's extra video is about rescaling variables. Earlier in the course, we learned about Z-scores. Z-scores are what you get when you standardize values in a vector, showing how far each value is from the mean. So imagine you've got a distribution. If you have a value here and the mean is here, it's pretty far from the mean, right? Z-scores give you a number for how far it is from the mean. They standardize a variable so that it can be easily compared. For example, we could grab all the data on towns in Japan in the year 2015 to see how Z-scores work. And as you can see here, I just ran this code that is downloading from the Japanese time series dataset, filtering just the year 2015, and it's selecting the income per capita, the population, and the median age in each town, as well as the name. And we can view them right here. Let's pull that up. All right. So I got to tell you, I don't really know what this value means. I know for a fact that this tells me that the income per capita in thousands of yen for Sapporo City in Hokkaido is 3,039. That's 3,039 1,000 yen per capita. I don't really know how big that is. I especially don't know how much bigger it is than in any other town. It would be nice if we could tell this. That's what we use Z-scores for. We can create a Z-score to tell us how extreme this value is. And we can do it manually using this code right here. So how do I do this? Well, I take my data frame and I mutate the rows. I mutate this value. I'm going to create a new vector, a new column in our data set called income per capita Z for Z-score. And I'm going to take the original income per capita. I'm going to subtract the mean of the entire vector, kicking out any cases that are missing, that are NA. And then I'm going to divide all of that by the standard deviation of that vector. In other words, how far from the mean are you in terms of standard deviations? How many standard deviations are you from the mean? Cool, right? So if we do this, we can run this function and save it into JP so that our new data frame has all of that in it. And we can view what we've done right here. So this is pretty useful. Look at this. We've got the original income per capita here, which was 3,039 for Sapporo. And we've got the Z-score for income per capita, which says that Sapporo's income per capita is 0.449 standard deviations from the mean. But Hakodate's income per capita, Hakodate is like a town to the south of Sapporo, it's pretty big. Its income per capita is actually 0.153 standard deviations below the mean. And when we look at these two values, they're not actually that far apart, right? 3,000 versus 27,000? 3,000 versus 2,700. They're really not very far apart. So Z-scores tell us a lot about our data and help us compare. Is this really extreme in this direction? Is it really extreme in this direction? We never would have known this otherwise. Here's the good news. There's a really slick and quick way to do this. We could do it manually. Didn't take long. We just took the value minus the mean, divided by the standard deviation. We can also use this function called scale. So for instance, I could create something called ZScore with scale. It's a new column in our data set. I could do it by saying, hey, take the income per capita for this row, scale it using the values in the column, and then just remind R that it's a number, that it shouldn't be read as a character. And once we do that, we can just select the variables we want to see. And yeah, here we go. We see that this very short scale function did the exact same thing and gave us identical results to the math that we did before. By the way, fun fact, all functions are math. You can do all functions in code. It's kind of cool. Anyways, great. So we made a z-score for income per capita using the scale function. Last but not least, z-scores are super, super helpful with regression models. Let's create a small regression model where we scaled each of the variables, the outcome and the predictor variables. So we can see me doing this right here. Income per capita, I'm mutating it so that I don't have to change the values actually in the data frame. So I'm changing it, and then I'm going to run the model. So I'm saying, hey, income per capita, replace income per capita with the scaled version of it. That's a number. Replace the median age with the scaled version as a number. Replace population with the scaled version as a number. And then, extra pipeline here, right? Now run this formula. Let's check it out. These alpha and beta coefficients are going to be different than the ones you normally get, but they're comparable. They're still valid. Technically, what's just happened is we've made our beta coefficients and alpha coefficients comparable. This tells us that as population increases by one standard deviation, by 1 unit, by 1 standard deviation, income per capita increases by 0.1529 standard deviations. Great, how obtuse. But we also know that median age, as median age increases by 1 standard deviation, income per capita decreases by about 0.534 standard deviations. Remember how I said you couldn't compare beta coefficients that use different units? Well, guess what? We just took care of the unit problem. This means we can compare population and median age. These are comparable units now. And I can definitively say that the effect of median age, according to our model, is larger than the effect of population. This one is larger and negative, and this one is larger and positive. This one is larger and negative, and this one is smaller and positive, right? Because the coefficient here is negative, but big. Coefficient here is positive, but tiny. So this is pretty cool. This means that the effect of population, nope, that doesn't mean that. This means that the effect of age is larger than the effect of population. This is why editing is important. Rescaling allows us to compare the effect size of different predictors on the same outcome. So I hope that you guys will definitely make use of this in your final projects. It's really, really useful if you want to compare, does this affect an outcome or does this one affect it more? If you have any questions, shoot me an email. Hope that you are enjoying the videos, and look forward to talking to you soon. Bye-bye.